show on the road. Right. So Alejandro Garcia will have special office hours this week because I will be away. But going forward, this is the schedule for office hours. Okay, so I'll have my office hours generally at this time in room 2500, which is in the corner of the building upstairs in the west corner of the building. And Alejandro will have his office hours on Mondays in
1160.
1160, is it?
Yeah.
Yeah. All right. Very good. All right. So, we set up some mathematical foundation. Let's talk about the physics. So, really, the subject, as we sort of discussed it when we talked about the units, is divided into sort of three categories. Electrostatics, magnetostatics, and electromagnetic dynamics. And they correspond to three different physical situations. Obviously, this is the most general of them, but these others are limited cases, and under those limitations, the equations of motion or the equations that describe the field equations are simpler, okay? So for electrostatics, we have static charges. And the current is zero. There's no current, everything, all the charges are fixed in space in some reference frame. Think about changing reference frame, of course, that says something, but we'll come back to that. Magnetostatics has a situation where we have steady current. So the current is not changing with time. Okay, that's the current density. So locally, at any point in space, the current density is fixed. So this is kind of this idea of steady current, and that's what we call magnetostatics. Okay, and dynamics is where we can have changing currents, okay? And when we have changing currents, what that can lead to is radiation. So electromagnetic radiation is the important change that happens when we start thinking about the dynamical problem, okay? So let's start from the very beginning. It's a very good place to start. And that's electrostatics, right? So as we introduce, remember the fundamental empirical law of electrostatics is Coulomb's law. Okay. And the Coulomb law, at its basis, thinks about 2-point charges, Q1 and Q2, and we set up some coordinate system. We have some particular point in space that we call the origin, and there is the position of charge 1, there is the position of charge 2, and there's the relative distance that goes from 1 to 2. And we know that the minus sign goes here because if I add this to this, I get that. That's how I always remember. Is it x2 minus x1 or x1 minus x2? Add this plus this, I gotta get that. Okay? Because the arrows go in that direction. All right. So, with that, we know that the force on 2 due to 1 is equal to Q1, Q2 over r squared, r hat, where we have chosen the units where that K1 constant is 1 and not 1 4 pi epsilon naught. Okay? So that's Coulomb's law, and as we discussed, we can also then say, well, charge Q1 is producing an electric field so this is the electric field due to 1 at some position, and the force on 2 due to 1 is charge 2 times the electric field due to 1 at the position of the charge. Okay? So this is how we define the electric field in terms of a chest charge and the force exerted on it. And so what this tells us is that if I have a point charge at position I'll call x prime. So we'll use primes to denote the positions of the charges. And I want to know what is the electric field at some position in space as the observer. So the electric field at position x coming from this charge at position x prime then is equal to the charge divided by the square of the distance from the charge to the point of observation, and it's a central force in the direction r hat. Okay? And r hat is the unit vector along the direction script dr, which is the vector over its magnitude. So sometimes this is written as x minus x prime cubed times x minus x prime. Is everyone clear what I just did? As I've written the unit vector as the vector divided by its length. Okay? So this is the electric field due to this point charge at this position as a function of the point of observation. Okay? Very straightforward. Now, importantly, very importantly, these are vectors in a linear vector space, so that we have the principle of superposition. So if I have multiple charges at different points in space denoted by position x prime sub I for the ith charge, then the total electric field in that case would be the sum over I as such. Okay? So that's the principle of superposition, which is critical to understanding the nature of fields, that this is a linear vector space, and thus we can superpose, that is, we can add together the fields independently from all of the point charges, and that gives us the total field at the point of observation with my big bad eyeball over there. All right? And we can then think about a sort of continuum picture. Of course, we know from the fundamental theory, we know that the fundamental units of charges do come in quantized units. There is a continuum, and there's no actual continuum, but we can approximate things as a continuum with a charge density as a function of the position of the charge, such that if I look at a little volume in space, the differential charge in this volume, which I call d cubed x at position prime, is the amount of differential charge in that volume. So this is the continuum limit, which fundamentally comes from coarse graining over something that effectively we call the differential, and so that we can call that a smooth peanut butter of charge, not chunky style. And so this then becomes the integral over the dq's, which is rho, so it's integral over the positions of the charge, so that, remember, the prime variables are the variables that define where the charges are, and rho of x prime, x minus x prime, x minus x prime cubed. Okay. So that's really the most general way that we could, given a charge distribution, find the electric field. Now, as we'll see a little bit later, this is a very hard integral to work with because the integrand is a vector. And so you have to think about all the components, and it's kind of typically, unless we have some particular symmetries, and we'll talk about that a little bit later, we rarely work with this form of the electric field, but this is the most general form that we could write down if we know what the charge density is everywhere in space. Okay. Right. So let's think a little bit about some of the properties. Of E in electrostatics. Okay. So let's just, again, let's think about for a point charge. And let's say it's at the origin. So my electric field is equal to Q over R squared R hat. Okay? So I have my charge at the origin, and as I can then think about, if I take a sphere centered at the origin, I can ask the question about the flux of the electric field through this spherical surface. Okay. So the flux of E through a sphere, say of radius, say capital R, centered at the origin, is that integral. So that's a surface integral, to remind you. And what the surface integral means is we take the vector field and we take the dot product into this vector dA, where dA is a vector whose magnitude is the differential area on the surface and whose direction is the normal to the surface. Okay? And so in this case, what is dA? Well, dA is in the direction r hat, because that's the normal to the surface. And the surface area of that is equal to, by definition of the solid angle, the square of the radius at that point times the solid angle, differential solid angle. And if we had spherical coordinates, of course, we know that we can write that as sine d theta d phi in the usual spherical coordinates, right? And so, given this particular electric field, this is the electric field at that point, on the surface when you do the surface integral. So the electric field at this point on the sphere is equal to Q over capital R squared R hat. Okay? So this then is equal to Q over R squared, R hat, that R hat is 1, times R squared d omega. And so the R squareds cancel, the Q is a constant, we get the integral over the sphere of the omega, and there are 4 pi steradians in the sphere, hence the flux of the charge through that surface is 4 pi Q. Okay? 4 pi means something, is the steradian, 4 pi steradians that this subtends. All right? Now, maybe I'll just come back here. If we didn't have a sphere, let's use it. If we didn't have a sphere, if we had a slightly misshapen potato, and the charge is somewhere over here, and I look at some point on the sphere, and there's some dA over here, then it's still the case that the differential area here is equal to whatever that radius squared times that solid angle. The solid angle will be bigger if I'm at a slightly, that's something that's not where the direction of the electric field is different than the normal, but it's still the case that whatever that solid angle is determines what the area of that patch is. So in general, it is the case that if I look at E at some radius dot this particular dA, it's still equal to Q times the solid angle. And so no matter what the shape of this surface is, this is my potato, that when I integrate over the closed surface, if the charge is inside the potato, then this is equal to 4 pi Q if Q is inside the surface. Okay? Now, if my charge were outside the potato, then what's going to happen is for the parts of the electric field that are on half the solid angles will have a positive contribution, and the parts of the field that are on have a dot product that is negative is going to have a negative contribution, and those two will cancel. And thus, the flux of the electric field is 0 if Q is outside. Okay? It's as simple as that. And thus, by the principle of superposition, we can just add up, if we have multiple charges, some of which are inside the volume and some of which are outside the volume, only those inside the volume will contribute a non-zero flux, and those outside contribute nothing. And so the more general expression for this through a closed surface is equal to 4 pi q enclosed, where this is the total charge that is inside this volume. Okay? And of course, we recognize that as the famous Gauss's law. Okay? Simple as that. Now, it's interesting to see what went into the derivation, which is almost nothing. The important points here were twofold, maybe three. One is that this is a central force, meaning that the force or the electric field is along the line of force. Now, that's what we call a central force, like gravity. Secondly, that we had a 1 over r squared, so that the field fell off with distance as fast as the area would grow, so that that factor canceled, and will cancel no matter what. And thirdly, the principle of superposition. Are there any other laws in physics that also obey those things? Classical gravity, right? Classical gravity is a central force that falls off, like, you know, the gravitational force between two masses falls off, and similarly, the principle of superposition holds. So there's also a Gauss's law for gravity, although we don't talk about it often. Very good. Now, if I want to, and I do sometimes want to, then we can write the total charge enclosed in terms of an integral over all space of the charge density. Now here, I could write this as prime, but I don't need to, because I'm not keeping track of two separate variables. This is a dummy variable. In the integral, it doesn't matter what I call it. Why throw a prime in there when there's no need for one, okay? So this is the charge enclosed. Maybe I want to mention just, maybe this is a good time to interject a way of formalizing the connection between the continuum of charges and the discrete point charges, okay? So, let's do a little aside. What is the charge density, rho, of a distribution with a point charge at x prime? What do you think?
Is that a delta function?
A delta function, right? So what does a delta function mean? So yes, so let's say we have a point charge of charge q. So this would say that if I have a point charge sitting at some position, which I'll call x prime, and I want to know what is the charge density at this position, then what we write is this is equal to a three-dimensional delta function. Oops. So what does this mean? So a three-dimensional delta function is the density of a point, okay? Let's maybe back up for a second. This is a shorthand for the product of three 1D delta functions where x1, x2 and x3 are the x, y, and z coordinates, okay? So this is a product where the x, y, and z coordinates of the point of observation are related to the x, y, and z coordinates of the point at which the charge sits, okay? So, first question for you. What are the units of a delta function? It's not quite. I mean, so what do we know about a delta function? Let's just remind ourselves that if I have a delta function, then what is true is that this is kind of the limit of a distribution like a Gaussian. Okay, so let's just imagine I have this kind of distribution centered, I'll call it big delta of x. Where big delta of x minus a, let's say, is where this is the width. Okay? Everyone should memorize the form of a normalized Gaussian. That, you know, back in the day, before the Eurozone, every European country had its own currency, and there was something called the Deutsch mark, no relation. And one of the bills had Gauss on it, because, you know, wouldn't you have famous scientists on your currency as opposed to whatever? And on that bill was the normalization of this Gaussian formula, and you know, you could just whip it out of your wallet when you're. So cool. It was so awesome.
They got rid of that.
Okay. So a Gaussian, I guess just a little side, a Gaussian distribution is defined by its variance, delta x squared, so the RMS width, that's the moment, the RMS distance from the mean, and A is the mean. And the Gaussian distribution is such that if I integrate it over all space, this is 1, okay? And of course, this height here, over here, is, you know, proportional to 1 over delta x, right? So the area under this curve is 1, right? It's a probability distribution. So now I ask you, what are the units of this function that I'm calling, maybe I should delta, let's just call it d. I guess there's too many deltas flying around. What are the units of this thing? It's 1 over the length, whatever delta x is, right? Because if I'm integrating this over x, and if x has the units of something, in this case length, then this function is a density, and it has the units of 1 over length. So a delta function has the units of 1 over its argument. It has to have that because when you integrate over it, it's dimensionless. So this thing has to have the inverse dimensions of that. That's always true. So 1D delta function is a density in physical space, okay? And the delta function is the limit as delta x goes to 0 of the Gaussian. That's one way. I could have many distributions that all limit to a delta function, but this is kind of the nicest one, okay? And so what will happen, of course, is that this thing gets skinnier and skinnier, and it goes higher and higher and higher, and eventually squeezes so that it only is non-zero at that point. So a delta function of x is 0 when x does not equal to 0 and infinity at x equals 0. Okay? And this three-dimensional delta function thus has units of what? 1 over length cubed. It's a 1 over volume. So that's why this is the density of a charge. Okay? So we should just then say that if I come back over here, if I have a set of point charges, then I would write this like that. That's the charge density associated with a collection of point charges that are positioned at these positions. And when I integrate it over this, what I will integrate, I only integrate over the enclosed volume that is enclosed by the surface, and it will pick off the sum of all the charges that are inside. So the delta function is a formal way of connecting integrals to sums. Okay? All right. Very good. So let's now return to Gauss's law. Excuse me, I should have brought my water. And remind ourselves that we can re-express this in a differential form, thinking about the local properties of the electric field and how it's changing at a position in space, okay? So we can, as you remember, we define the divergence of a field, say the electric field, at some position x, which we write, or we can actually express through the divergence theorem in terms of the, excuse me. I'll be back in a moment, I just need to get some water. I'll be back, right back.
Wow, it sure is physics in here. Me too. Oh, really? Great. We're still in like I didn't know you had that. Still, I didn't either. Very I forgot I had this shirt. Our shirt, sorry, my seat was taken. I understand. The one to be very third row. Well, you remember what Yogi said last class? The great distribution versus seating arrangements? That doesn't count if you try to sit the front row. Oh, was that? He's saying if there's an extra seat in the front row, you charge. Yeah, basically.
All right, let's get back into it. So, the divergence. The divergence is defined as I have some position and I have some little surface that's going to sniff out. There's some surface S and there's some volume D that is enclosed around that surface, and I take the limit as there's a little differential volume goes to 0 of the flux integral at that position divided by delta V.
What is that symbol with the arrow pointing to the sphere?
That's a scripty S.
S.
That's the surface.
Surface.
So that's the surface that is enclosing this little differential volume. Okay? So that's the definition of the divergence. And of course, what that tells us is the divergence theorem. That's to say, if I look at the overall space, if I add up this, that says that I can, for a finite volume, calculate the flux integral through the closed surface by adding up within the enclosed volume all the little divergences. So the divergence tells me something about how much local flux there is. If I were to put a little surface around that point and ask how much stuff is flowing in and out or out of that, that's what divergence tells us. And of course, this is equal to, according to this, 4 pi, the volume enclosed, of d cubed x rho of x, according to what we wrote down from the integral form of Gauss's law. And so from this, since this must be true for an arbitrary volume, the integrands must be equal. And thus we get the differential form of Gauss's law, which tells us that at any point in space, how much divergence there is of the electric field is equal to whatever the local charge density is, times 4 pi. So these are the integral and differential forms of Gauss's law. So whatever the local charge density is, tells us what the divergence is. Okay? All right. Let's just check something. So let's look at the point charge. And let's calculate the divergence. So the electric field, let's consider an electric field of a point charge at the origin. Well, no, it's a point charge at x prime. Okay? So the electric field, we've written this many times now. Well, let's just, actually be easier to deal with this. Let's put it as the origin. So my electric field is this, or equivalently, that, right? Let's calculate the divergence of the electric field. How would you do that? So you have kind of two choices. We can do this, and this is a point I want to emphasize here. when we're thinking about our Einstein summation equation and stuff like that, we're always thinking about Cartesian coordinates. If we have curvilinear coordinates like spherical coordinates, we have to be kind of careful, and we have to go into our textbooks and so forth, or maybe we remember what the divergence is in spherical coordinates. Here, this only has an r component, and in spherical coordinates, this is equal to 1 over r squared d by dr of r squared e sub r. Okay? Which is what? E sub r is here, multiplied by r squared.
R squared is canceled.
Yep, 0. Okay? Let's just for fun use Einstein's summation convention, because if we're on a desert island and we forgot, you know, what this formula is, and we had to calculate the divergence to get off Gilligan's Island, then we'd have to use Einstein's summation convention. Okay?
That's how this is useful.
Exactly. I'm on a certain generation. I really couldn't. All right, so let's remind ourselves, because it's fun, that the divergence of E in Einstein's summation convention is that, right? And the ith component of that, so that's d sub, the partial respect to the ith component of this scalar x sub I. That's the ith component of electric field. Okay? So what is this? This is equal to, I have the q comes outside, and then I use the product rule. That's 1 over r cubed di xi plus xi di 1 over r cubed. You with me? All right. What is this? I'm summing over I. So I take the partial with respect to xi and then sum over I. So what is that? 3. Because it's partial of x with respect to x plus partial of y with respect to y plus partial of z with respect to z. That's what that means. Which is each one is 1 plus 1 plus 1, 3. Okay? And let's just do a little aside over here. The partial sub I of 1 over r cubed, using whatever rule in calculus, this is minus 3, the partial I of r over r to the 4th, right? Whatever rule that is in calculus. And this is what? Well, this is what?
Do we not need to convert R to?
We do.
Okay.
So now we have to convert this into right? And that's going to give me 2 powers of this. So this is going to be minus 3 xi over r to the 4th. So when I put that all together, what I get is q times 3r cubed minus 3 xi over r to the 4th, which is r squared. Oh, I missed an r here, times r. Did I screw this up? Let me do this again. Partial respect to I of that gives me, okay. It's harder than I thought. Minus 3 over r to the 4th. then I got a half,
Oh.
right? And then I got delta ij xi, and then I get two of those over r, because this is to the minus 1/2 power. So this becomes xi over x to the 5th, which cancels. It was easier in turbulent currents. I'd never get off killing because I'm really terrible, right? The reason I brought the 1 over r, because when you take the derivative, this goes to the minus 1/2 power, right? And the minus 1/2 power puts it in the denominator. All right, but what's the real point of this exercise? The real point of this exercise is that what we just found is that del dot E equals 0 for a point charge.
In all space?
Well, interesting question. How is that possible? Because we know that this has to equal 4 pi this if this encloses the origin. And that's supposed to equal the integral over all space of this. But we just said this was 0. What gives?
Maybe we're ignoring the origin.
Right. The point here is that the derivative doesn't exist formally at the origin because the electric field blows up at the origin, okay? So what it must be true so E blows up at the origin, okay? And because E blows up at the origin, del dot E is not defined. And we can formally define it by, it must be the case that this is equal to whatever the del dot E is rho of x. And what is rho of x for a point charge at the origin? Which blows up at the origin. Okay, so this is the formal way in which we can make sense of the differentials through the use of the Dirac delta function. If my charge is at x prime, then del dot E is equal to, 4 pi. 4 pi delta. All right, good. So, let's continue about our properties of the electrostatic field. We just saw something about how much it diverges from points. The divergence from points are determined by what the local charge density is. The other feature of vector fields is how they rotate around closed contours, okay? So let's think about the rotational properties of E in electrostatics. So let's just, for simplicity, just start with the problem of saying I have the charge at the origin, I have my XY plane, and I have the Z axis here.
Two Y's.
All right, so now if I just look in the XY plane, it's easier because God knows I can barely draw perspective. Here's a circle, here's my charge, here's the electric field coming out, and here's a curve which has a differential length element, which is the length of that element and the tangent to that curve. So for the circle, that is equal to the radius of the curve times a little azimuthal angle d phi in the phi hat direction. That is what that little length segment is. Okay, where phi is the angle in the XY plane. Yep.
Is that a real term, DLT vector?
Yes.
Okay.
So my t is the tangent,
Okay.
as opposed to the normal that we had in the context of the flux equation. Yeah.
So this is electrostatics. What is indicated by the arrows, the direction that you're writing the actual?
This is the electric field, and this is.
Oh, this is the field.
That's the field.
Okay.
Okay. So what we're interested in is what's called the circulation integral, which is the integral of the electric field around a closed curve. Now, in this particular case, it's trivial because the electric field is perpendicular to that, and that's 0. Okay? But it's true in general. You could do a little bit of geometry. If I move this curve up on the z-axis, and I took all, there's going to be a cosine angle, but you added them all up, it again would all add up to 0. I did an easy case because I'm lazy, but this is generally true for electrostatics. Okay. Now, as you remember, we can also think about in the same way we define the divergence in terms of the sniffing out how much flux there is at a local point. We can think about the circulation at a local point and define the curl of E as the limit as a surface area goes to 0 of the circulation integral over the area where I have some point and I have some little curve C and an area enclosed, little delta area. So I'm asking the question, how much does the field circulate around a point as I shrink this curve to 0? That's called the curl. Yeah.
What does it mean to circulate?
This to circulate is the size of this circulation integral. This closed contour loop is saying how much does it, if I add up the electric field times the tangent, how much do I get?
Okay.
So that's telling me how much the electric field, or any field, has a finite rotation around this curve.
So circulation is 0 for a perfect circle around the point of interest?
No, because this might, for the magnetic field, this is not going to be 0.
Yeah, okay.
Right? But for the electric field, it is.
Okay.
At least in magnetostatics. So, the curl is actually a vector, and we define it in the direction normal to the surface by the right-hand rule. So if I have a surface that is, say, the potato chip, I like potatoes, that is enclosed by this, then the normal, this is what we call an orientable surface, because it has an orientation like a Mobius strip. I can write by using the right-hand rule and seeing how my, because you know, we're righties, most of us, not everybody, I'm sorry, lefties. But you're in shape because you can write and do the right-hand rule at the same time. I always have to put down a chalk, and that's always annoying when I get it wrong. So the curl is in the direction of the normal, okay? And so from this, we remember Stokes' theorem. Which tells me that around a finite curve, the circulation I can get by adding up all the curls. So what we have then for the electrostatic field, because the circulation integral is always zero, that is to say that the electrostatic field is irrotational. What that says is that the curl of E is zero for electrostatics. Okay? It's equivalent to the integral form, which says that the circulation integral around any closed curve is zero. All right, so now, as we have started to learn in looking at Helmholtz theorem, every field is defined by its curl and its divergence. There's one caveat to that having to do with boundary conditions, which we'll get back to, because there's an assumption here about the boundary conditions that the field goes to zero at infinity. If we had, but you know, there's nothing out there at infinity, so for the moment, we'll take that as our boundary condition. So we have the field, we have defined the field in terms of its curl and its divergence. And so in some sense, this is the whole story. These are the field equations. Now the way we solve these field equations is instead of using the fields themselves, we use the potentials. As we know, if I define some field as the gradient of a scalar, then its curl will be zero. And it goes the other way. If its curl is zero, then there exists a scalar field such that E is the gradient of it. Now, by convention, because this will relate this to potential energy, we have this minus sign here. So this is by convention that we'll talk about more next time of a scalar field. Okay. If it's true that E is the gradient of a scalar, then it's obvious that its curl is zero. Maybe it's not immediately obvious to you right now, but you can do it using Einstein's summation convention. And you can think about this as the cross product of a vector with itself is zero, right? A cross A is zero. So del cross del is zero, okay? But what is phi? Well, we can get phi by defining phi of x, which we call the electrostatic potential, or sometimes just potential, in the following way. Where phi at xg is 0. And that any point that for which the potential is 0 we call ground. Okay? So we can define the potential here, the electrostatic potential, as the line integral from some point we're calling ground to our point of observation. That line integral depends on my point of observation. Ground is arbitrary. We choose it however we like to be the point that we call the zero potential. And we do this line integral. And by the fundamental theorem of calculus, then, when I take the derivative of this, I get the integrand. Okay? So given, now, why was this important that the curl was 0? Because the curl was 0, the circulation integral was 0. And because the circulation integral is 0, that means that this line integral is independent of path.
So we can just draw a straight line and make our
We can know whatever path we like. And that has to be true if this can be a well-defined function. Okay? And you can see that that's true because if I do this minus that, I get 0. Therefore, this line integral equals that line integral. The path integral, or the integral over the line, is independent of the path. Okay? And that allows us to define this as a well-defined function that only depends on x and what we're calling ground, but not the path. So it had to be independent path so that we can do that. So that's the interrelationship here between the curl being 0 and the field being the gradient of potential, is that I can write down the potential as a path-independent line. Yeah?
Is it usually the case that we'll choose ground to just be the origin?
Not necessarily. We often choose it the opposite. We choose it often at infinity, because that's a natural place to do that.
Ground can be infinity.
Sure, it can be an infinity. So let's actually do that. So let's think about the potential of a point charge at the origin. Okay, with ground at r equals infinity. So here's the origin, here's the charge, and I'm out here at some point. Okay? The electric field is Q over R squared R hat. The potential is equal to minus the integral, and we might as well choose our line integral on a path on it at just going out radially, keeping R and keeping theta and phi constant. So I'm going to take my line integral along the our axis and integrate from ground, which is at infinity, up to R. Okay? So I'm going to call that R, I'm going to call this R prime, and then I'm going to get minus Q d R prime over R prime squared from minus infinity to R.
What did you replace E dot R with?
I replace the electric field with this,
Oh, I see.
and I'm doing it over R, and this is a dummy variable. Okay, so the integral of 1 over R squared is minus 1 over R. And so this is equal to Q over R prime from minus infinity, or from infinity to R. I already did that, so from R to infinity, and this then is Q over R. This at infinity, potential is 0. Okay? So, generally speaking, if I have my charge at some point x prime, and I'm asking what is the potential at R, if my charge is sitting at x prime, then the potential of a point charge sitting at x prime is Q over the distance to the first power of that. Okay? So that's important. The electric field is goes like charge over R squared. In the direction, the potential goes like 1 over R, or the distance from the charge. And if I have a collection of charges, I would sum them by the principle of superposition, and by the continuum, this then is equal to this, with the potential being 0 at infinity. We have to choose where ground is in order to define the potential. Okay? So this expression is easier than the one we had for the electric field, because there's no vectors in the integrand. And often, when we're solving these problems, we solve for the potential rather than solving for the electric field, because this is an easier thing to deal with. And then at the end of the day, we take the gradient. Okay? All right. Last thing I want to discuss now. So now we wrote this down starting from Coulomb's law and working and saying that was the empirical law, and here is the solution that we got. I mean, Coulomb's law gave us the electric field, and they integrated it, and this was the field. But we want to look more generally at this, where we didn't necessarily have Coulomb's law, but instead we had the field equations and derived this solution. Okay? So let's look at the solution to Maxwell's equations. In electrostatics. Here's how we do it. We start with Maxwell's equations. Del dot E is equal to 4 pi rho. Del cross E is 0. We can solve these equations using the potential. Because del dot E is 0, it is the gradient of potential, and by convention we take that to be minus the gradient of the electrostatic potential. And thus, when we plug that into this equation, we get this equation, that The Laplacian is del dot del. The Laplacian of the potential is minus 4 pi rho. That's a partial differential equation. The partial is the x squared of phi plus the partial with respect to y squared, etc. And this equation is the Poisson equation. So if we can solve the Poisson equation, we can get the potential, and given the potential, we can find the electric field. And that's what most of electrostatics is. Okay? Now, how are we going to solve that equation? The way we're going to solve that equation is to use the principle of superposition. And we use the principle of superposition. It says that this charge density at rho is actually a sum of point charges, or really an integral of point charges. Each point charge at position x prime has a charge density that's a delta function. So I can write this formally in the following way, and let's think about what it means. Why is this? I guess I forgot to remind you of a very important property of the delta function, right? In 1D, if I integrate the delta function with respect to a function of x, it replaces the function by the value of the delta function. Everyone remembers that, right? So is this then clear? That when I integrate this with respect to x prime, I replace x prime with x. Okay. But what does it mean sort of physically or geometrically? What this is saying is I can think of the charge density at some point as being made up of all the point charges weighted by their strength. So this is like adding up a bunch of point charges. So what that tells me is that if I can find the solution to the Poisson equation for a point charge, then I can find it for anything. If I can make it there, I can make it anywhere, right? So what I want to know is, what is the solution to the Poisson equation for a point charge? If I know the solution for a point charge, then I can make it for anything, because it's just add up the solutions for all the point charges weighted by their strength. And that's called the Green's function. If you never knew what the Green's function is, that's what it is. The Green's function is the solution for a point. And if you know the solution for a point, then you can make it for anything, because you can superpose anything in terms of a bunch of points. So, So g of x at x minus x prime is the solution to Poisson's equation for phi of x given a point charge of unit strength at x prime. So here's the problem. We have a point charge with strength 1 at x prime. I want to know what is the potential at my point of observation x. And the equation it solves is the Poisson equation, where rho is the charge density of this unit point charge at x prime. What is the charge density of a point charge at x prime of strength 1. It's just a three-dimensional delta function. Okay? And what we know that this solution is, we just found, and we're going to do this, we're going to invert it, but we know the solution for unit point charge is here. So this tells us something important that you're going to need for probably for your homework. That the Laplacian of 1 over x minus x prime I'm sorry, this should be minus. So, how is this possible? Well, we're going to do the mathematics about this next time, right? But from the Poisson equation here, in order for this to be self-consistent, this must be the Green's function, right? The Green's function associated with the solution of potential is a solution to this equation. And we're going to solve that equation next time and find indeed that the solution is what we have. Okay? And so what this tells me is that rho of x minus x at x, I can get by adding up the solution for all if I have the solution for a point charge, then I can get the solution for any one by just weighting it by the strength of the charge at that point. Another way of saying this is I take the convolution of the charge distribution with the Green's function. But what this means, sort of intuitively and physically, is I'm just superposing the solution for every point. If I know the super point and I know the strength of the charge at that point, then I just add them up. That's what the convolution is doing for us here. Okay. So we'll conclude that next time. Yeah, question?
Is there like a unity maybe for point charge?
It's a unit point.
In this case, I'm taking q equals 1. So the Green's function is for a unit strength. Okay? But the q is here. So let me write this in a slightly different way. Let's put the so this is the strength of the charge at that point. And the total potential then is equal to the potential associated with a point charge weighted by the strength of that charge. dq times g is the adding up all the potentials associated with all the point charges. That's what that convolution integral is doing. You should really think about the Green's function in terms of the principle of superposition. If I know the solution for a point, I can make anything because I can make that distribution out of a sum of points and I just add them up. And I use the delta function to do that, to turn the sum into an integral.
That's different from Green's theorem, right? Green's function?
No, they're quite related. We'll talk about that soon, yeah. But it's intimately related. But the Green's function is a powerful tool for solving differential equations using this. Exciting. Yes. See, I was excited.
Yeah.
It took me a while for my coffee to kick in. All right, everyone. Have a good rest of your day.
Thank you.
Yes.